Thanks, Evgeny, and thanks for having me here today. So I'm going to talk about, as Evgeny just said, invisible gamma-ray pulsars and where to find them in observations and how to look for them in population synthesis. So this talk consists of two parts. So the first part is part of my PhD work, which is using data from the Fermi Gamma-ray Telescope to look for these invisible gamma-ray pulsars with some stacking techniques. And the second part is to use COMPAS to do population synthesis to match the try and match the observation with some modeling. Okay, so my collaborators are my PhD advisor Tim Paglio and some other faculty and students. They were very wonderful back there. And also Simon Stevenson, Debatry, and Team COMPAS, which a lot of you are actually here today. So thanks for all of your help and collaboration on this work. All right, so we're going to start with talking about the Fermi Gamma-ray Space Telescope. I'm being informed that not many people here are very familiar with gamma-ray observations, so I'm going to spend some time on that. So Fermi Gamma-ray Space Telescope, which is illustrated here, it was launched in June of 2008 and went into survey mode in August of 2008. It has two instruments on board. The first one is a gamma-ray burst monitor. So some of you may use that to look for gamma-ray bursts associated with, let's say, gravitational wave events and other FRB events, but I don't actually use that instrument. What I use is the Large Area Telescope on board, or LAT for short. It has two steradian field of view, so that covers about 1/6 to 1/5 of the entire sky, so large area indeed. It has been surveying the gamma-ray sky nonstop in the energy range of photons from about 20 MeV to up to about 1 TeV. So 15 years almost of surveying the entire sky nonstop. So we have this very beautiful all-sky map in gamma rays that's produced by Fermi. So we have this thin disk in the center of the sky. Of course, that's the galaxy. We have the galaxy center very bright, very shiny, and we have these cloudy areas. I think Rho is around that area, and we have our usual gamma-ray bright pulsars. We have Vela, Crab, and Jaminga. You can all see these sources very brightly shining in gamma rays. So far, Fermi has discovered over 7,000 gamma ray sources over its, well, that was published in its 12-year catalog a few years ago. Doesn't sound like a lot, but if you compare to where the old gamma ray space telescope come from, that's actually a very large number. Another very important milestone in Fermi history is that it received a total of about 1 billion photons as of 2020. And again, not a large number when you compare to other wavelengths where you get literally buckets of photons wherever you point the sky. But for gamma rays, that's actually a lot of number. So a lot of our issues are actually small number statistics, which compared to billion photons is quite a lot. I'm also going to briefly talk about LAT in particular because the data analysis relies on us knowing the structure of LAT and how it actually does the data analysis. So it's, again, not your typical telescope. It's practically a particle detector, right? So when the gamma ray comes in, it hits the conversion foil and it gets converted into pairs of electrons and positrons, which moves down the particle tracking detectors and then eventually hits the calorimeter. Right, so this whole process can give us time of arrival, directionality, and the energy of the incoming gamma ray photons. Right, so we have all those information for each individual photon. Knowing all of that, maximum likelihood analysis then is designed to determine the source of each photon. That helps us to assign photons to a source or an event and tell us more. If we get more from that particular source, we can construct spectrum, we can construct light curves, and all of the other important information about a particular source. And this process is actually particularly important in complicated regions, such as the center of the galaxy. If you remember from the previous plot, it was very bright. So I zoomed in on that for you. You can see that the center here has over 3,000 photons. Again, not a lot, but it's quite bright in gamma rays. There's also gassy areas in the plane, a lot of gas clouds in the plane. That's also complicated. We have to very carefully assign photons to which source that it's either the background or the cloud or the source that we're interested in. And also, a lot of these bright gamma ray sources are often variable, so that's also something we need to take into consideration. So this is actually a new animation that I just found last week that Fermi published. Shows you with the sun moving on the galactic coordinates how fast and how much each of these gamma ray sources would vary in their flux. So the size of each of these pink dots represent the actual gamma ray flux of a source. Okay, so I'm going to pause for a little bit and see if there's any questions regarding Fermi and the Large Area Telescope in general. Yeah?
What are all these sources?
So most of them are AGNs and pulsars. And some other, yeah, most of them are actually AGNs, blazars, all of the similar kind. All right. I'm going to then move on to quickly introduce, I'm not going to go into details and tell you how to do the actual data analysis. That requires a few days of workshops. I'm just going to quickly talk about what is being done when we look at the data analysis pipeline. So it can be broadly broken down into 3 sections. We have data selection. So from the maps we just saw earlier, we have all sky data in gamma rays, so we have to choose which area we're interested in and focus on that. And we also need to choose our time range that we're interested in and the energy range of the photons that we're interested in as well. So that completes the actual first step of the choosing data. And based on the location of the spacecraft and the inclination of the spacecraft, we actually can also choose the quality of the photon incoming. So if you have something coming, if the spacecraft is pointing there and you have something coming from this direction, it's probably not as good of a recorded photon as you want. So you can discard that in your analysis. And then next step is to do calibration. So it takes into the consideration of the instrument response function, the lifetime of the observation, and the exposure that we observe for that patch of the sky. And that can convert the photon counts into actual flux that we're interested in. And then the last step is to do the modeling. So we have some initial models from the catalog. We can add sources that we're interested in that are not already in the catalog and feed that model to the data. And with the maximum likelihood estimator, we can then estimate the best fit spatial or spectral parameters of the source we're interested in using this method. All right, so given this is also very important in explaining the stacking in a little bit, so I'm going to, bear with me, show you some equations. So this is how the actual maximum likelihood for Fermi is designed. This was also used for Fermi's predecessor, the IKELIHOOD telescope, which is why the reference is 1996, but it's being kept for Fermi. So with few photons, each photon coming into the Fermi telescope detector can be considered as a Poisson distribution instead of a Gaussian distribution, which is why we see this Poisson form. Right, so this likelihood is constructed by multiplying the Poisson probability of receiving photons of each pixel. Right, we compare the actual observed photon in each pixel with the model photon counts that should be there in each pixel given our model. So that model consists of backgrounds, catalog sources, and the sources you add into the in your model that's not already in the catalog. So by doing that, we get our likelihood function. Right, the next step is obviously to maximize the likelihood function, but we don't want to maximize that directly. Right? The multiplication of hundreds of terms is very hard to take derivative. What we do is then take the log of the likelihood function. That gives us the summation of hundreds terms, so it's much easier to take the derivative of that. Right. Also ignored a few constant terms here. If you see the difference between these two forms, that's why. Right, so we have this easier form of function that makes things a bit more, slightly more, less complicated, I guess, to deal with in the computational side. And by maximizing that function, we can then get all of the best fit parameters. Either you want the location of the sources you're interested in, or you want the actual gamma ray spectrum parameters of the source you're interested in. It spits out that. And the byproduct of this whole process is that we can define the test statistic, or the TS value of a source that we're interested in, which is defined here as twice the difference of the maximum likelihood, log likelihood value of these, subtracted from the log likelihood value of the null hypothesis, meaning if you take that source out of the model completely, you can get the test statistic. So in Fermi observation, these test statistic, or TS value, roughly reflects the significance of the source. In a hand-wavy way, it's slightly more complicated than that, but usually when we have a TS value of about 25, that means we have a 5 sigma detection. We also can construct or calculate the TS value of noise, or empty sources, or test sources, however you want to call them. They don't come out to completely zero. They would actually follow a chi-square distribution over 2 with the appropriate degree of freedom. So here, the histogram is some noise population that I made up that's not supposed to have any actual signal, compared to a chi-square distribution with 2 degrees of freedom. You can see that roughly matches. Right, so right now we're only talking about each individual source, and what we're stacking are a lot of sources. So how does that actually work? Right, because we're looking at log of likelihood functions, we simply just add them up. Right, so we can essentially just take the equation that we looked at before and add them all up for n sources. And what happens now is that we can then consider the population of actual sources and the population of controls, or noise, or empty fields, and this can be considered as the TS value of, or the maximum likelihood value of sources, and this part can be considered as the null hypothesis. So we can, by comparing 2 different populations in this way, we can essentially determine if there's anything there within the noise that we want to discover. Right, so that's one way to visualize it. This is simulated data with a source with signal-to-noise ratio of 0.5, and that's 50 regions of interest, or ROIs, added together. And each pixel would actually tell you the TS value of, if there's a source there, what's the TS value of that. So we can see that at the center where the simulated source is, there's a huge bump after we add 50 of these snapshots together. And the rest of that, we don't really see that boost in signal. So this is what we're trying to do. We're essentially trying to get that excess of TS value either in the physical space or in the parameter space of the source that we want to, or the source population that we want to look at. As I said, this is part of my PhD project, so this was performed on quite a few different types of objects, so that includes nearby flare stars and pulsars, clusters, luminous stars, interacting binaries, and possibly some more as well. If you're interested, you can ask me about any of these. I have actually slides for all of them. But for today, we're going to focus on pulsars. Right, I'm going to pause here again and see if we are all at the same stage before I move on to talk about what I do with pulsars. All good? Great. This is one of our undergraduate collaborators, and that helped with the work in pulsars. Pulsars are highly magnetized, fast-rotating neutron stars that are remnants of massive stars' evolution after supernova explosion. It was first detected in radio in 1967, and the story behind that, I figure everybody is probably familiar with it, that the supervisor got the Nobel Prize, but Jocelyn Bell Burnell didn't, but she practically won the respect of everyone for her lifetime. That's also a good story. And the first gamma-ray pulsar was detected in 1974, not too long after that. At this point, there are over 3,000 pulsars detected in the entire sky, but only about 300 of them are discovered to emitting gamma rays. Right? So we have 90% of the population that possibly should emit gamma ray that are not detected yet. Another reason that detecting pulsars in gamma rays is important is that pulsars' electromagnetic emission is powered by the spinning down of a pulsar. So the pulsars experience magnetic braking. The fast spinning is actually gradually slowing down, and that makes that actually converts these rotational energy into the EM emission that we see. And most of that EM emission actually should come out in gamma rays, at least for more powerful pulsars. And that's also, there's also a lot of arguments and different models in what the emission mechanism of pulsars should be. And we don't really know for sure, but I'll try to explain with what I can understand. Right, so here we have the neutron star over here. At somewhere near the surface of the neutron star, the density of particles is quite low, but the magnetic and electric fields are very strong. So the particles are accelerated into relativistic speeds very fast, and it can start to move along the magnetic fields to emit curvature radiation. So the curvature photons then are extremely energetic because the field's very strong, can very quickly decay into a pair of positron and electron through pair production. And then the secondary particles then move along and emit more energetic photons, either through synchrotron or curvature photons, and this keeps being converted into next generation particles. The next generation particles gets more photons, and this is essentially a scenario of particle cascade happening until we reach far enough away from the surface of the neutron star where the particle density gets very large, and that would actually close off the acceleration field. One of the issues that people aren't sure is exactly where the gamma ray photons coming from around pulsars. So people are pretty sure that the radio emission of pulsars come from the polar cap regions, right? So that's the magnetic axis of the pulsar. That's the rotational axis of the pulsar. So people are pretty sure that the radio emission comes from these regions. But there are different scenarios for geometry of gamma ray photons coming from the pulsar. So some people argue that they come from the outer gap areas, which are these thin layers that goes from the surface of the pulsar to the light cylinder. So the light cylinder is the location where the co-rotation speed is at the speed of light, and it goes along the magnetic field lines and extends very far from it. So some studies suggest that most of the energetic gamma-ray pulsars actually emit in these regions. And there's also two-pole caustic regions. I'm less familiar with this model. I think some people also refer to that as the slot gap model as well. And there's also some recent suggestions that the magnetic reconnection around the light cylinder would actually eject a lot of particles into this current sheet outside of the light cylinder that can also emit gamma rays. So the point is that there's a lot of uncertainties in the emission mechanism theories of gamma ray pulsars. But anyway, what we are going to do is to try to find out for these pulsars that are seen in radio but not in gamma ray, what they behave, how they behave, what they look like. So here you can see the all-sky map of the gray dots being all of the radio pulsars that are recorded in the catalog. The blue ones are the gamma ray pulsars, and the green ones are the ones that I'm going to look at. So you can see that there is a gap running through the middle. That there are no green points. That's because I want to avoid the complicated region that is the galaxy and to have a better signal-to-noise ratio. So that's cut at about at 20 degrees in the galactic latitude. So by choosing this galactic latitude cut, it's actually also giving us a region in the parameter space when we look at the pp dot diagram that's over here. Right? That's quite different from the observed gamma ray pulsars. So this plot is, for those that aren't familiar with it, is a plot that's plotting the spin period of the pulsar on the x-axis. So when we go towards the left, it's rotating faster. When we go towards the right, it's rotating slower. And the period derivative, so the rate of pulsar spinning down in the vertical axis. Right. So at the top part of the plot, the pulsars spin down faster. So the change in their spin period is faster, and at the pulsars at the bottom part, their spin period is changing much slower. So that's more stable. We can also see that this essentially divides the pulsar into two groups. We have a bunch here. We have a bunch here. These are our canonical pulsars. So that's, I think that's what was, that wasn't in the title, sorry. So these are the canonical pulsars that are believed to be slightly younger, and they're more energetic in general, particularly those ones in the gamma ray pulsar, regions. And we think they're younger because they fall into this younger region of the characteristic age, which is represented by this set of the diagonal lines. Right, so they have slightly lower characteristic age. And this bunch, we call them millisecond pulsars. That's because they have spin periods in the ranges of a few to a few dozen milliseconds. And they also have much lower spin down rate. That means their spinning is quite precise. Right, so our latitude cut actually transfer into this region of the pulsars that we're interested in, which are slightly older in the characteristic age and slightly less powerful when we look at the spin down energy rate, spin down power, spin down luminosity, however you like to call it. That's how much rotational energy they lose within a second. Right, so that part they have higher spin down power. In this part they have lower spin down power. Right, so this range of pulsars we're interested in seems to have less spin down power and are older in general. Right, so there are 360 pulsars over there that we chose with the cut. So what we did was to assign each of these pulsars a power law with exponential cutoff spectrum. And that looks like this. So that's the cutoff energy. That's the power law index before the cutoff. So what essentially the spectrum does is that it goes as a power law, and then it drops out very fast after the cutoff. So the cutoff energy is chosen to be about 830 MeV. That's typical for a gamma-ray pulsar. And we did all of the analysis that I mentioned earlier in parameter space. So the parameters are chosen to be the gamma-ray flux and the power law index before the cutoff. So so this is for all of the 360 pulsars stacked together, and we can see that it has a index before the cutoff at about 1.6, and it has actually the flux converts to about I think 3 times 10 to minus 10 photon per square centimeter per second. Well, when we look at the control, it has a much larger, more negative index. That actually means that it's actually behaving like the background. So the background of the gamma ray observation is extremely soft. That means even before it reaches the cutoff, it's starting to drop very fast. So we have these two distinction between the background and the pulsars. That is very good. And we can also look at what the pulsar spectrum looks like. So that, and we just need to bin the data into smaller energy bins and do the same thing for each of the energy bin. We can see the pulsar spectrum stacked together in 3 different energy bins in the blue data points. The blue curve here is actually just a sanity check on if this result is physical. So we can't perform timing analysis or spectrum analysis on them because they are not actually individually detected. So what we did was to take some inverse competence scattering model to see if we just have a whole bunch of energetic particles scattering off the photon field of the surface of the pulsar, it would create something similar to what we see, and it does, which is good. We also compare this result to some to the average young pulsar or slow pulsars, which is here, and the average millisecond pulsar spectrum. So also note that these are scaled down a little bit, 2 orders of magnitude. They're actually much brighter than the stacked pulsar, which is expected because these are not detected. It means they're much less bright. And another thing that we can look at is the relation between the gamma ray luminosity and the spin-down power. So this is important in a few slides when we talk about the pop-synth. So the gamma ray luminosity is defined like this. We have 4 pi d squared, as usual, the gamma ray flux, and we also include a beaming factor, which is normally assumed to be 1 for gamma ray observation. So we have the luminosity in the vertical axis and the spin-down power in the horizontal axis. And the blue dots are all of the Fermi pulsars, and the green data points are our stacked pulsars there's luminosity. So as you can see, there's some trends there. There's a heuristic relation where people assume that the gamma ray luminosity is proportional to the square root of the spin-down power, or some people go a little bit extreme, saying that all of the gamma ray luminosity comes from the spin-down power. But it looks like this is slightly more likely here. And so that's the end of the pulsar observation. So before I move on, is there any questions you want to ask? Yeah, Ilya.
So what about all the systems that have an apparent luminosity greater than the spin down power?
Very good question. So the initial thought we had is that the distance measurement of the pulsar is not great in the catalog, because some of the pulsars are in regions where there's a lot of interference to get a good dispersion measure to estimate a good distance that can actually, in fact, result in a factor of a few to factor of 10 difference. So that transfer to one or two orders of magnitude difference here. And some people also think the beaming factor, assuming to be 1, is not a great thing to do for all the pulsars, but that goes down into the geometry of the emission mechanism, which is a little bit uncertain. Yeah, real.
So in the first movie you showed, many of the gamma ray sources look very variable, but here are you just picking out sources that like they're static or like?
So pulsars are variable at a very small scale, right? So a few seconds, milliseconds, right? So if you smear it out into 10 years of observations, it actually, even if you look at it within day to day, it actually shouldn't change that much. Right? Actually looked at crab as an example. If I just observe it in a day and compare it to the next day and to the next day, it stays pretty much constant. Yeah. Sorry, I didn't hear.
You're not choosing any of the bursty sources like soft gamma repeaters or?
No. Right. Yeah.
Yeah. So when I think of radio pulsars, I think of very narrow beams, so that that isotropy factor would be very different from one. What are the? Can you just say sort of approximately what are the pulse profiles in gamma rays look like? Are they sharp? Are they sort of more broad than radio?
So I can show you that after the talk. There's actually a centralized page where it shows the gamma ray pulse profiles of these pulsars, but it varies. So it has some very sharp peaks, like the radio pulsar. You also have extremely broad peaks, like the others. Yeah, I have some things on that as well. All right, so we are now seeing this population of individually undetected pulsars in the data and roughly how they behave. How can we confirm that? So that comes with the use of population synthesis. In addition to that, doing population synthesis of pulsars can also give us insights on the birth locations of the pulsars, how the pulsars should look like when they were first born, and all of these different questions. There are some previous studies that did slightly similar things, like this Dearson 2022 paper, but they actually don't include full-fledged population synthesis. They just assume that the pulsars behave in a certain way when they were born at a certain place in the galaxy and do that. So what I do is a little bit different because I track the entire evolution history of the stars, and then that converts into how the pulsars actually behave and how it should interact with the companion or interact with the other environmental properties too. So the population synthesis code I use is COMPAS. So some of you here are very familiar with this. Right, so COMPAS was initially developed to track the gravitational events coming from double compact objects mergers. And this is also good for looking for pulsars, because pulsars are a product of massive star evolution. And massive stars are, majority of the massive stars are born in binaries. So this is a very good use of the code. And COMPAS is developed based on the single star binary star evolution model from Gerald Hurley in 2000 and 2002. And code is optimized to rapidly evolve a lot of binary system within a short amount of time. And it's also there's also new features added to the code constantly that can track different types of binaries that people are interested in. To use COMPAS to produce pulsars, I have to set certain parameters. Right, so there are hundreds of parameters that can be set for COMPAS. I'm just giving you a few examples and some categories that can be set as parameters. So for individual binary systems, we can set their mass, we can set the initial mass function, their metallicity, and how many binary systems we want to look at. So in these examples I'm going to show you later, there's this is how they're set. So mass range from 5 to 150 solar mass. The metallicity is the solar metallicity. There are 10,000 systems I'm looking at, and we can set the orbital properties. We can set the common envelope properties, supernova kicks, and a prescription for remnants. And we can also set the birth parameters for pulsars. So this is just arbitrary model that I have chosen. That's sort of a base model for COMPAS with birth period range distribution. Same thing for the magnetic field at birth and magnetic decay timescale. So after we set that, then COMPAS would generate binary systems. So here, as an example of the type of system that I'm interested in, it would generate a massive star, which is showing here in blue, and a low mass star showing here in red. Right. So the massive star goes supernova very fast, and it would disrupt this binary. So the low mass star would be lost, and we are then just left with the pulsar emitting either in radio or in gamma ray. We're going to decide that later. And the pulsar lives for a certain amount of time until it slows down so much that it reaches what we call the death line, that it cannot be observed emitting radio or gamma ray emission anymore. So we have to assign a birth time for the system, let's say at 12.8 years, and hopefully we should make the observation before the death of the pulsar. And if we make the observation after that, we are not actually able to see this system. So we're making the observation at 13 gigayears, which is roughly the age of the galaxy. And after we do this for our 10,000 systems, well, they don't necessarily all turn out to be pulsars. So we're having much fewer pulsars in our results. We can then put the pulsars through some dynamical evolution to locate them in the galaxy and move them around the galaxy according to some descriptions of the gravitational potential and function of the galaxy. So this is done with a code called NIGO, so that's short for numerical integrator of galactic orbits. Right, so it takes these three descriptions to combine our galactic potential energy, including an exponential disk, a plumber sphere as a bulge, and dark matter halo. This would distribute the pulsars around the galaxy, and combining with the kicks they receive when they were born through the supernova explosion, it would move them around the galaxy. And of course, all of these pulsars are assumed to be born in the thin disk as the massive stars. Right, after we do all of these and combining them with making the observation, we can then decide if a pulsar is observable in radio or in galaxies, in gamma ray. So that's done in two parts. I'm going to talk about radio first. So we're observing radio emission from pulsars using the code called PSR evolve. So this code I'm using is from the modified version of Orlowski and their group from 2021, but it was originally developed by Donia Matthew Bales and Lorimer way before that. So this code would take the location of the we're looking at in the sky and tell us if the sky temperature, tell us the sky temperature and the dispersion measure at that location based on the survey telescope. So I'm assuming that all of these pulsars are going to be observed with the Parkes multi-beam all-sky survey, and and we can use previously estimated property of the pulsar to determine their radioluminosity and convert that into the radial flux and compare that to what PSR evolve is telling us and if that pulsar can be observed or not. We do sort of similar things with gamma ray, but there's nothing written already for gamma ray, so I just did my own things. So here I can calculate the gamma ray luminosity using, again, the properties of the pulsars themselves. I can either use some empirical relation, which is what I showed you from my plot with the pulsar's luminosity versus the spin down rate, spin down power, or there's also more sophisticated theoretical estimation like this, which tells us the gamma ray luminosity relation between the gamma ray luminosity and the magnetic fields and the spin down rate, spin down power of the pulsar. We have now the gamma ray luminosity. We can convert that into the gamma ray flux, and we can then use the sensitivity map of Fermi. So right now I'm only using, just testing things out. I'm using some 2D step functions to simplify this, so that when the pulsar falls into a certain region, we can determine if it's beyond the sensitivity limit and can be observed. So there are some improvements there to fully implement that map we just saw. Okay, so that's pretty much what I did with the simulation and the results. So let's look at some plots. So remember, this is just a very early results, and by choosing some very random COMPAS models, and so this is not yet very refined results. So what we are looking at here is the gray being the overall underlying population, the blue ones being radial pulsars that can be observed, and the red ones are gamma ray pulsars that can be observed. And again, for a sanity check, I just plotted if we choose choose a 20-degree galactic latitude cutoff, we can have the pulsars that we're going to stack in this part of the PP dot diagram, and indeed they are, so that is good. We can also plot their location in the galaxy. So there are some good features and there's some bad features on this plot. The good thing is that we have pulsars all across the sky. There's a concentration around the galactic center, but we are missing these bits here. And that's because our underlying star population that we chose from the galactic estimator earlier heavily centers on the galactic center, and that's why we're missing the parts that's actually opposite of the galactic center. All right, and we can also see that there's some cumulative distribution functions of the physical properties of the pulsars. We have the period comparison with the catalog in blue and the model in red, and that's for the period derivative. And this is for the E dot, the spin down power. This is the radial flux and the gamma ray flux. So we can see that pretty much right now we can only say the radial pulsars are observed similarly to the catalog, and the gamma ray pulsars are not entirely, but again, early results, still trying to refine the model. So hopefully in the future it will get much better with the fitting. And similarly, we can look at the locations of the pulsar with the galactocentric X, Y, and Z. Not so great, especially when we look at the galactic latitude distribution. We're also missing a lot of pulsars in the plane. Right, so there's a lot of improvements to do still. Set COMPAS runs with different parameters, and we'll have to improve the distribution of birth locations of pulsars so they distribute more realistically compared to the catalog, and we have to perfect these selection effects for gamma ray observations. So that comes to the end of my talk. So just to remind you what happened during the talk, I talked about stacking methods developed for Fermi data and used that stacking methods to reveal population of undetected pulsars and characterize their gamma-ray emission. And I also talked about how we can use population synthesis, such as COMPAS, to explain the observed undetected population of pulsars. And hopefully we can also update COMPAS soon enough to implement millisecond pulsar formation and to also complete that part of the work as well. And I will leave that there and take more questions.
In your simulations, I mean, you see this ramping up of sources towards the death line and the sharp cutoff. Of course, natural from the model you're assuming, but that's not what's observed.
That's not. So that was my point, because this is just some arbitrary model that I just set to test out the pipelines. Yeah.
But with your model, you will always get this ramping up. So the question is, I mean, so observationally, the systems sort of more peter out as you approach the death line, right? So how are you trying to study that? This is why we did mention some of those mix.
Yeah, I haven't thought about that, but I think in my head, possibly defining different distribution of the pulsar's birth properties might help.
Well,
and
more the evolutionary properties, right? Because evolution slows down as you go in that direction, and therefore that's why you get this ramping up effect.
Yeah.
So there must be something about the visibility.
yeah, that's also, I guess, the improvement on the possibly on the radio selection effect is also going to help, because you don't really see similar trends in the gamma-ray observations. I think here the gamma-ray pulsars are quite dispersed in here, but the radio is kind of crowded around here. Yeah, I have to think about that, because this is, as I said, very early on in the. Yeah, because the pulsars move like this, and the cutoff is around here. So
You don't see any down there. So.
yeah, that's because we really can't observe them. Yeah.
I have potentially quite a naive question, but when I look at the PP dot diagram, I would think that the gamma ray radiation would gamma ray pulsars would die before the radio component dies, because you're having a lower spin down parameter and slower periods, it's less energy. And I just wondered if you could elaborate on why there seems to be the radio and gamma ray die at the same time.
I guess I wouldn't say they die at the same time.
Well, it has to do with the acceleration process that breaks down with that.
Okay.
And it's that acceleration process that produces both the radio and the gamma.
Yeah, so I think for now it's sort of a choice in the codes, so that I can have an idea of roughly where to cut off the simulation, so that they don't fall into a region that's neither going to be observed by radio or gamma ray. The gamma ray pulsars here themselves, they are let's say, I wouldn't say they reached some death line there themselves. Yeah, but hopefully when we have larger samples, that would actually end up with filling out this nicer than what it looks like right now. Yeah, so I actually, if we go back over here, so people used to think that this range, this E dot is some sort of gamma-ray deadline, because there were practically none of the gamma-ray pulsars observed down here, but you can see there are some actually blue dots down here that's kind of covered by the green dots, but they are there. So in realistic terms, I think that's possibly just sensitivity issue. Yeah.
So for your COMPAS population, why do you choose to use solid analyticity?
Because when we look at canonical pulsars, they relatively short-lived, right? So the supernova explosion happens very fast, and the pulsars reach deadline also relatively fast. So if we choose some faraway metallicity and trace this back in time, essentially we're not going to be able to observe the pulsar anymore because they cross the deadline and they cannot be observed. So it makes sense to just choose the solar metallicity.
So just a comment related to Rena's question, that if I just believe that plot saying the luminosity is roughly proportional to the square root of the E dot, then actually the lower E dot system should have a higher proportion of gamma rays. So this lower UI, when you lower the spin down energy, it looks like you might have a proportionally stronger gamma ray. Just if I just believe this. My question was, so are all your gamma ray pulsars single, or did you choose any that were in binaries?
Do you mean for this or for COMPAS?
For this, well, for the observation.
For the observation, it's a mix of everything.
So you do have binaries as well?
It does have less than a handful of binaries.
Okay. Yeah. Would you expect the gamma ray emission to be the same in binaries?
So when I actually do the comparison between these and the COMPAS models, I'm actually going to take away the binaries from these because right now COMPAS can't do millisecond pulsars or X-ray binaries. So I can update you on that when I get there.
There's no questions. Maybe I can ask something very basic, because I think so probability is still basic, but I think in the observed sample you didn't have any millisecond pulsars compared to the observed one, right?
8 actually.
Yes, so you have, but in the simulated sample you didn't have any of those yet, like a longer period, right? Yeah. So why is that so?
It's just because COMPAS right now can't produce millisecond pulsars.
Okay, but do you believe that millisecond pulsars form by some other channels, maybe in some different environments?
No, it's just there's a little issue with the code at the moment and can't produce millisecond pulsars. We're going to fix that. Yeah.
And since we stole my question about binaries, I think I have no more questions prepared for you. So if there are no further questions, let's thank Robert again.
Thank you.